Okay, it's necessary for me to back up a tad. And let's look at this animal right here. This is a state ket. State of what? It's the state of a system. It's getting really abstract now. For instance, let's choose a system. As simple as possible, an electron. So that's the state of an electron. And it doesn't have to necessarily be associated with spin, but it can be associated with spin. We could have the state vector of position of an electron or the momentum of an electron. But those are more complicated, and we'll get to those later. But right now, if we just say the state of an electron and we consider that spin is one property that can be measured, that's easy. Momentum, mass, position, we can do those things. But those are different properties than spin. Similar, they're intrinsic, but how do we know what the components of that vector are, or what's the basis of that state? And the basis of that state is determined by what kind of measurement we want to make. So the measurement basis that was chosen could be on the z-axis, aligned z-axis, non-aligned z-axis. Or it could be x-axis, aligned x-axis or non-aligned x-axis. Or we could even do y-axis, aligned y-axis or non-aligned y-axis. Those would be different basis vectors that we choose for that. The state of a system has certain vectors that determine the state, those basis vectors. But look what I do here. If I multiply the state by any real number, it doesn't change it. It's still the same state. So what would that do to the vectors inside? Well, that would change the vector's length, wouldn't they? And those lengths, or it could even change the direction. Like a -1 here could change the direction of that. Now what does that mean really? What does the state represent? It really represents what we call a ray, which is represented by a vector with any length, any direction along that length. Now we can also say that this animal that we introduced earlier, this e to the I phi, which represents the complex phase, I can even multiply that times the state, and it doesn't change the state. So all of these things are equal, which I guess that means we could factor these things out or add things to those basis vectors, and it would still be the same state. Now, while I've got this thing up here on the screen, let's look at what that really means. E to the I phi is the same as cosine of phi plus I sine of phi. And that means that if we go to phi of 0, cosine of 0 is 1, sine of 0 is 0, so that just leaves 1, the real number 1. This leaves the real number -1. This leaves the imaginary number I. This leaves the imaginary number -I. And then if we have something that involves both real and imaginary, then we can choose an angle like pi over 4. Then we have a mixture between these things. So this represents the numbers that are indicated when we do this complex phase. But as long as that is multiplied throughout all of the basis vectors, then it doesn't change anything about the actual state. Now that we've kind of banged around this idea of a state, let's talk about the state for a spin property, and we have a z and a minus z. In other words, aligned or not aligned. And we can say that there's a ratio of all the rays with respect to this definition of the z basis that fall into this category. Cosine theta over 2, sine theta over 2, and this phase difference, if there happens to be a phase difference. The probability of z, or the aligned axis, is we can take the Bra vector of the z and create a bracket with the state. And this will project the probabilities. Now, one thing I want to stress that I keep getting messed up on is these two bars are magnitudes. And when you have a magnitude and you have some complex numbers, you're going to have to use the complex conjugate transpose. Now, isn't that a mouthful? Let's see how we can determine a probability by taking the z Bra vector and projecting it on the state. So, here's the Bra vector. Here's the state, cosine theta over 2, just like up here. And the plus z, see there's the Ket part of the state. Then we have the Bra vector over here, and the e to the I phi sine theta over 2, and this z non-aligned. So I hope you can follow through all that, but let's now go through this and see how we come up with an answer. We take the Bra z vector, the Bra vector of the z aligned, and that gets combined with the Ket vector over here, and z and z, if you take the inner product of a bracket with the same vector, you just get 1. And if we take this Bra vector and bring that over here to the z non-aligned, then those two are mutually exclusive. You can't be aligned and non-aligned at the same time, so that just becomes 0. So what are we left with? Well, that 0 chops out that. This just becomes 1, so we're left with cosine theta over 2, and the magnitude of cosine theta over 2 is just that. That's a real value. So then we square it, and that's what we expected.